Welcome back to this lecture series on pulse width modulation for power electronic converters. We are looking at the last module of this lecture series and which is actually on pulse width modulation for multi-level converters, basically 3-level converters. So, we had these various course modules which we had covered earlier. This would be the first set of course modules like module 1 and module 2 which essentially covered certain basics of power electronics, looked at DC-DC converters, DC-AC voltage source and current source inverters, and also looked at multi-level converters including neutral point clamped and flying cap capacitors and so on, and particularly neutral point clamped converters we were looking at. Then we are looking at applications of voltage source converters like motor drives and static reactive compensator, active front end converter and so on, grid connected applications and the motor drive applications. So, this is on the first set of modules, and subsequently we are looking at PWM generation in this second set of modules. We looked at certain basics of this PWM method such as Fourier series waveform symmetries and the effect of waveform symmetries on the harmonic components, and then how you would generate PWM waveforms at low frequencies where you switch the inverter at only let us say 5 times or 7 times or 9 times the fundamental frequency, and then how you would do it when you are switching at a fairly higher frequency, that is your fundamental frequency may be several tens of times, say 30 times or 40 times the fundamental frequency. So, for example, if you have a motor drive and the maximum speed, the maximum fundamental frequency is 50 hertz, if you are switching it at like 3 kilohertz or 4 kilohertz, the switching frequency is much higher than the modulation frequency, and in such cases you use these kind of triangle comparison and space vector based PWM methods normally, where you compare them with 3 phase modulating signals against a common triangular carrier. Here you use the space vector approach. Instead of the 3 phase modulating signals, you have one revolving voltage space vector. You sample that every subcycle and that gives you the voltage command, and you try to realize that by applying the various vectors of the inverter for appropriate durations of time, and these two are equivalent to a large extent. You can have continuous PWM methods or bus clamping PWM methods implemented through either of the approach, but there are certain advanced bus clamping PWM methods which are space vector methods, as we have observed on numerous occasions before. Thus, we regard space vector based PWM to be more general than the triangle comparison PWM. So, now this is all done in the context of 2 level inverters. So, like the entire PWM generation in the context of 2 level inverters. Again, there is this analysis in the context of 2 level inverters. Here, considering a high switching frequency case, we try to see how to evaluate the current ripple, the RMS current ripple there, and then how to look at the DC link current is something that we looked at, and how to look at the torque ripple. This is for low switching frequency and high switching frequency cases. So, the principles are pretty similar, and here again evaluating inverter loss. These were certain things we saw in the third set of modules. These are all again in the context of 2 level inverters, but all these are extendable to 3 level inverters also. This line current ripple is basically what we do is we integrate the error voltage or the voltage ripple. That is something that you can do in the 3 level inverter also. Now, except that the error voltage vector will be shorter here. So, the error voltage will be lower, and because there are more number of vectors available, your error is lower, and therefore, the line current ripple will be lower in a 3 level inverter. And similarly, the DC link current, that the way you evaluate it by multiplying the load current and switching function of device, here also we can evaluate it in a similar fashion. So, again torque ripple also in the current ripple part, if you look at the q axis component alone, which is orthogonal to the fundamental flux, then you would get a measure of torque ripple. So, the basic principles are essentially the same, and the inverter losses, it is a little different here because you may have 2 devices conducting concurrently, and your switching loss would involve VDC by 2, but the same ideas are still valid. The switching loss, you need to come up with E on and E off of the devices, and then you can certainly calculate them now. So, again these are all in the context of 2 level inverters, and mostly they could actually be extended to 3 level inverters. Then here we looked at certain advanced issues, for example, inverter dead time. So, because of the switching transition taking a considerable time, we introduce this dead time, that is we are not switching the 2 devices in a leg exactly complementary, we delay the incoming device. After the outgoing device has been turned off, the incoming device is turned on after some time delay TD, and so that has its effect on the fundamental voltage and all that. So, this is there certain amount of non-linearity gets introduced here. The reference voltage is no longer proportional to the, I mean, output is no longer proportional to the reference. Of course, the ideal output is proportional to the reference, there is a small error voltage that gets added up, and in this module we tried to see how much is that error, and that is error in the fundamental voltage, and we also tried to estimate the harmonics, etc. We actually found that the error can be approximated, the average error in averaged over carrier cycles. You could look at this effect of dead time as like a square wave for continuous PWM methods, or some kind of quasi square waves for the discontinuous PWM methods. So, what you can actually do to compensate for that is to add the inverse of this square to the modulating signal. So, that is a way to compensate for that. So, this is certain kind of non-linearity coming up there, that is you are modulating at a particular modulation index, you are producing an output, and that output is slightly different from what you want, plus there are also low frequency distortions getting introduced in that. Your modulation frequency may be 40 hertz or 50 hertz, let us say 50 hertz. This also introduces low frequency distortions like 250 hertz or 350 hertz in the inverter output. So, that is something about dead time, and over modulation is where you want to go from linear modulation all the way till 6 step mode to increase the DC bus utilization from 90.7% of 6 step voltage to 100% of 6 step voltage. So, we looked at this from the triangle comparison and spur sector point of views. Well, all these are also extendable, these ideas are extendable to 3 level inverter. What we would essentially be doing in these few lectures is to look at these. We look at these, like this particularly this triangle comparison and the space vector PWM, we would like to see how exactly we can extend that. In the last lecture, we looked at extending sine triangle PWM particularly to the 3 level inverter, and we would look more about it now, and today we will also discuss how do we do it from the in the space vector based approach, produce PWM, and probably the next lecture we would focus on some aspects of this analysis, how you would analyze the line current ripple, and as a consequence how you could possibly design some hybrid PWM techniques as we did in this particular module for 2 level inverters now. So, let us get going with this present module. So, in the present module, which would comprise of 3 lectures, this being the second lecture, we would look at, we would be reviewing the topology, neutral point clamped inverter topology. Actually, we did it in the last lecture, and we also looked at the definitions of pole voltages, line to line voltages, line to neutral voltages, and the mathematical equations relating them, and we looked at the inverter states. There are about 3 to the power 3, 27 inverter states produced by the 3 level inverter, and they produce 19 distinct voltage vectors. So, we looked at those, and then we looked at sine triangle PWM with 2 level shifted carriers, and who could be in phase, or there could be with some phase difference or out of phase, etc. And we ended up the last lecture just beginning to discuss about the switching sequences for in phase and out of phase PWM, and in fact I had asked you to look at this as a home exercise, just try to find out how consider some particular switching cycle and see what kind of switching sequence you would get with in phase and out of phase, are they different and in what sense it is different. Anyway, we will do it today, and we would look at these 3 nearest voltage vectors for any given reference vector. So, in most of the PWM methods what we do is, like in 2 level inverter, you have a reference vector, you apply 2 active vectors, one on the clockwise side, one on the anti-clockwise side, and one null vector. Here you have more options available. What we do is we choose the so called 3 nearest voltage vectors, and we synthesize the average vector by time averaging. And what happens is, when you use sine triangle PWM with in phase, it automatically chooses the 3 nearest voltage vectors. That is something we will see today. And it is not the sine triangle PWM, sine 3 phase sinusoids you can compare with 2 level shifted in phase carriers. Then instead of sine wave you can also add common mode. For example, you can add third harmonic to the sine, and you can have the those 3 phase modulating waveforms with common mode added compared against these level shifted carriers, and you can do this. And instead of third harmonic injection, you can also go for bus clamping PWM, which we did in the context of 2 level inverter. Now, we can do it in the context of 3 level inverter. So, these are certain things we would focus on today, and we would possibly try and look at how do we do space vector based PWM, and how from some difficulties that we might have in doing space vector based PWM. It is really an extension of what we did in the 2 level case, but here 3 level case the number of vectors are more, and the choice of vectors is higher, and so you have certain issues coming up we will see how they can be addressed, and one way to address them would be to look at a 3 level inverter as an equivalent 2 level inverter in every extent of the fundamental cycle. If you have fundamental cycle divided into 6 parts, I mean 6 portions, you call each of them as a extent or a sector. So, in each extent you can see that a 3 level inverter can be viewed as an equivalent 2 level inverter, and then we would see further issues on what exactly comes out of that, and pivot vector which is yet to be defined, and how do you do this conventional space vector PWM. And there is one other issue that you would have is DC voltage unbalance. We may not have a very long discussion on that, but we will briefly see why there is a DC voltage unbalance in the context of 3 level inverter and how that could possibly be handled. Alright. So, again DC link current we would quickly look at how we can extend our knowledge of calculation of DC link current for 2 level to 3 level case. And so, we will look at this bus clamping PWM and all that from now the space vector point of view, and importantly we would look at this advanced bus clamping PWM. What we did for 2 level, we will try and see how that can be done for 3 level inverter, and we will get started with have some very preliminary discussions on how we can analyze the line current ripple using this idea of stator flux ripple, and how it is possible for us to implement some to design some hybrid PWM methods. So, this would be the content of this module, and as I mentioned today the focus today would be on the switching sequences and this other third harmonic injection, bus clamping, etc., up to somewhere here on how you could possibly control a 3 level inverter as an equivalent 2 level inverter, and the remaining portions would be more or less dealt with in the next lecture now. So, this is the second lecture in this module. This is lecture 38 of the 40 lecture series. Second lecture in the 13th module we would call as PWM for 3 level neutral point clamped inverter 2. Alright. So, voltage source inverter. So, you have 3 phase load, the load is presumed to be inductive. So, you see that these are all poles. So, that they are the load terminals are connected to the poles of the switch, so that the inductive circuit will not get opened out, and then the throws, you have the DC voltage connected across the throws. So, you have that, and you switch, and this is how you really connect that. You have a capability of connecting the pole either to plus VDC by 2 or minus VDC by 2 to the top or bottom here. And so, it is possible for you to apply alternating voltages here, and you do this as an inverter here. One thing that we realized here was this is for DC AC conversion, where you use single pole double throw switches in a 3 level. So, and this is how they are actually electronically realized. You have 2 transistors, and each transistor has an anti-parallel diode. It can conduct in both the directions, and it can block voltage with a particular polarity. So, we realized that we could also use a single pole triple throw switch. In fact, we can have single pole and n number of throws, 5 throws, 6 throws, etc., where each throw is connected to certain voltage level. So, now there is an intermediate voltage level plus VDC by 2 minus VDC by 2, in between there is 0. This actually helps us in maintaining better waveform quality as we saw before. So, we can for example, the instantaneous voltage earlier could only be plus VDC by 2 and minus VDC by 2, now it could be 0 also. So, earlier the VRY, the potential between these two, can only be plus VDC or minus VDC or 0. Now, it can be plus or minus VDC or plus or minus VDC by 2 or can be 0. So, it gives you better choice, and the output waveform has a chance of following the desired sinusoidal output more closely. So, that is what it leads to. So, this is how we realize a single pole triple throw switch. We discussed this in a lecture or 2 earlier in the first module. So, this pole to the top throw, these 2 switches are on, we found that it is going to be that. I also did this in the last class, I am not sure if that is required now. In any case, if I have my S1, S2, S3, S4, and this is VRO, if I have my S1 and S2 on, S3 and S4 are off, then I will have VRO will be equal to 0.5 VDC. On the other hand, if I have S1 is off, the outermost device is off, here also S4 is off, S2 and S3 are on, then I will have 0. So, in this case, as I mentioned to you, the current is in this direction, the current would flow like this. On the other hand, if the current is in a different direction, then it would flow like this. So, if the S3 and S4 are off, S1 and S2 are on, then you are going to get minus VDC by 2. These are the 3 different pole voltages, and you can very easily understand and quickly realize that this and this are complementary. The same way you can see this, I am sorry, let me change that. This and this are complementary, that is what we have said here. S1 and S3 are complementary and S2 and S4 are complementary. So, you need 2 independent signals. Earlier we needed only one signal in the case of 2 level inverter, here we needed 2 signals here. And this is where I am just showing 2 legs connected. This is, you can probably consider it as a single phase 3 level inverter, where you can connect a single phase load here. Just I have shown 2 legs here. Now, here I have shown all the 3 legs. So, this is what is really your 3 phase 3 level inverter, which is what we are considering now. So, this is the load terminal R, this is the load terminal Y, this is the load terminal B, and this is the DC midpoint O. This is the DC positive, this is negative. You have a voltage of VDC by 2, here you have a voltage of VDC by 2. Okay. So, we presume the load is something like this. The load is R, Y, B, and the load has certain neutral which is not electrically connected anywhere. This is what we understand now. So, this is apart from the idea of single pole triple throw switch, it can give you, there are more number of voltages are possible at the pole, and therefore, the waveform quality is better. Now, when you really want to block this voltage VDC, now you have 2 different devices available to block this. So, in some sense this is like the series connected IGBTs, but in the case of series connected IGBTs, the voltage sharing will have to be ensured. There could be parasitics, there could be other things spread in the characteristics of these devices, which may may not lead to equal sharing of voltage. This may be little more, this may be little less, etc. But here it has, there is one advantage which also, like as I have pointed to before now. For example, let us say this voltage, that is these 2 are off, when these 2 are off. So, they are blocking some voltage, and let us say this voltage is greater than 0.5 VDC. If it becomes greater than 0.5 VDC, what will happen? This will dip below O, then this will come into conduction. So, this clamping diode makes sure that when they are sharing, the voltage across this is really no more than VDC by 2. So, it partly solves the problem of voltage sharing, and that is one of the advantages that we have here. And now, so you can handle, for example, by through 2 devices the voltage blocking capability. So, if you have 2 devices, your voltage rating of some rating V, so it is as good as having a device of voltage rating 2 V. So, you can actually realize a higher inverter with a higher DC bus voltage. So, one area where they are actually applied these 3 level inverters are so called medium voltage drives. That is, when you have motor drives, now let us say this 3 phase load, I have just shown it like a passive load, it could actually be an induction motor. So, it could really be an induction motor connected like this, R, Y and B. So, here you would normally have motors, there is some voltage rating. So, in India the motor rating, the voltage ratings of motors are typically like 400, 415 or 440 volts, 50 hertz, that is what you have. Maybe in some other places you will have 110 volts 60 hertz or 208 volts 60 hertz, and some depends on the standards in different places. So, the voltage rating is typically hundreds of volts. Now, let us say it is about 440 volts, you will need a DC bus voltage, the DC bus voltage may be like 700 volts. So, many a times in the Indian conditions you will need for this 400 volt systems, you may need something like 600 volt to 750 volt, not really more than 800 volt, and you handle them using a voltage source inverter with a device, I mean a 2 level inverter's device rating may be 1200 volt. Now, you may have these motors which are rated a few kilovolts. So, if it is rated hundreds of volts, you call them as a low voltage motor. If it is rated in kilovolts like 1.1 kV, 2.2 kV etc., you call them as medium voltage motor drives. So, for such medium voltage motor drives, this becomes a very good option, because you have lot of 1200 volt devices available, 1700 volt devices may be available. Of course, there are devices of higher ratings available, maybe up to 3.3 kV, which are called high voltage IGBTs and all that, but they become rare, or or they may be more expensive compared to the voltage ratings of this now. So, this allows you, for example, to use two 1.2 kV devices. So, you can use 4 1.2 kV 1200 volt devices now. Like so, with 1200 volt devices, you get the advantage as though you are using 2400 volt devices are being available to you. So, your DC bus voltage need not be 800 volts, your DC bus voltage could be 1500 or 1600 volts. So, that is possible with 3 level inverter. That is one of the reasons why it is actually one of the major applications of 3 level inverter. This is the medium voltage motor drive. So, here what we have is, so you can also use it in the low voltage conditions. So, that is what I was mentioning yesterday when I was saying this. It has the advantage of medium voltage drives, because it uses 2 devices to block certain DC bus voltage, and when it is switching, you can see that each switch handles a voltage of VDC by 2 only as against VDC. So, sometimes in the low voltage applications also, like for example, certain grid connected applications, it becomes advantageous, because the switching loss tends to be a little lower than the 2 level inverter. So, some studies have been made in the literature, where you may find some papers on comparison of 2 level inverters and 3 level inverters. And so, one of the thing that shows up is in the low voltage applications also 3 level inverters are applicable, they are advantageous compared to 2 level inverters, particularly when the switching frequencies are high, because they are able to reduce the switching losses and give certain advantages in terms of the overall losses. That is one of the advantages, because they produce better waveform quality, the filtering requirement is low, that is another advantage. Alright. So, when we look at this, let us look at the equations pertaining to that. This is the instantaneous voltage, as I mentioned, it can be plus or minus VDC by 2 only for a 2 level inverter. Now, it can be 0 also. So, VYO VBO. So, VRO is VRO minus VRY is VRO minus VYO, as in the case of 2 level inverter. Again, VRN is 1/3 of VRY minus VBR as in the case of 2 level inverter. Here we assume a balanced 3 phase load. So, because of this additional 0, your VRY is you also have this plus minus VDC by 2 possible. In the case of 2 level inverter, your possible values of VRY are plus minus VDC and 0. Here it is plus minus VDC by 2 also possible. Then you have VRN. So, what happens is plus or minus 2 VDC by 3. This is what is possible with 2 level inverter, and also plus or minus VDC by 3 and 0. These are possible with 2 level inverter. Now, you have this VDC by 2 also, and plus or minus VDC by 6. So, these are certain additional voltage levels that become possible because of your additional connection, your the third point that is available, your ability to connect the load terminal to the DC midpoint gives you these options now. Alright. So, the other thing, as I mentioned yesterday, is, for example, if you want 2 VDC by 3, there is only one possibility, or let us say VDC, there is only one possibility. VRO has to be plus VDC by 2, VYO has to be minus VDC by 2. But if you are looking at plus VDC by 2, VRY is equal to plus VDC by 2, there are 2 possibilities. One is VRO can be plus VDC by 2, VYO can be 0, or VRO can be 0 and VYO can be minus VDC by 2. So, these are 2 possibilities here. Here you will have multiple possibilities to come up with that. So, for getting VRY equal to 0, both VRO and VYO could be equal to plus VDC by 2, or both VRO and VYO could be equal to 0, or both VRO and VYO could be equal to minus VDC by 2. So, when you come to the lower lower and lower voltage levels, you see that can be realized through many switching states, through more number of switching states, and these possibilities are the ones that give you many ways of designing PWM methods and so on and so forth. So, this 3 phase pole voltages, 3 phase line to neutral voltages VRN, VYN and VBN, they satisfy the condition VRN plus VYN plus VBN is equal to 0. So, they are not 3 independent quantities, they can be represented in terms of 2 independent or orthogonal quantities, which are called V alpha and V beta, and you can arrive at V alpha and V beta from these by saying V alpha is VRN cos 0 plus Vyn cos 120 plus Vbn cos 240, and that would be equal to 3 by 2 times Vrn. Then you can say V beta is equal to Vrn sin 0 plus Vyn sin 120 plus Vbn sin 240, and that turns out to be root 3 by 2 times Vyn minus Vbn. This is the 3 phase to 2 phase transformation. So, when you do this, you would get that for a 2 level inverter. So, these are the the 2 level inverter has 8 inverter states. There are each leg, the top can be on or bottom can be on, and there are 3 legs. So, 2 to the power 3 8 inverter states, we designate them as 0 1 2 3 4 5 6 7. So, now 0 and 7 correspond to what are called 0 states, minus 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 meaning all the top bottom devices are on, here all the top devices are on. In both cases the load is shorted, and therefore, the output voltages are 0 and the voltage vector is 0. In all the other cases there is some transfer of power between the between the DC side and the AC side. So, you have it like this. So, you have these were your 6 active vectors, all of them are of length VDC, that is given our conventions, the length is VDC and this angle is 60 degrees. So, the way we arrived at these voltage vectors for 2 level inverter, the same way we can arrive at the voltage vectors for 3 level inverter as we discussed yesterday, and which we can quickly again do today. So, we have accounted for there are 3 to the power 3 is equal to 27 inverter states. Out of 27 inverter states, we have accounted for 6 inverter states. These lead to voltage vectors of length VDC. These vectors are identical to what has been there. Then you will have 3 vectors, I mean 3 inverter states, minus 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 0 0 0 and plus plus plus, all these lead to a null vector. So, instead of 2 0 states in a 2 level inverter, you have 3 0 states now. All the 3 pairs of top switches are on or bottom switches are on, or the 3 pairs of middle switches are on. So, these are the things now. So, let us take the other combinations. Let us say you take plus 0 0. Now, plus 0 0 is very similar to plus minus minus. You can see a lot of similarity here, whereas in plus minus minus your voltages are line to line voltages are VDC 0 and minus VDC would be the line to line voltages. Here it is VDC by 2 0 and minus VDC by 2 are the line to line voltages. So, it is similar except VDC getting reduced to VDC by 2, the line to line voltage getting reduced to VDC by 2 rather than VDC, and therefore, what happens, this produces a voltage vector of magnitude 0.5 VDC. Now, if you take the other state, for example 0 minus minus, this also produces the same set of output voltages, the line to line voltages as plus 0 0. So, you can see that these 2 states produce a vector of magnitude 0.5 VDC, and they are aligned with this vector plus minus minus, corresponding plus minus minus. Okay. The same way you can look at the inverter states plus 0 or 0 0 minus. So, they all produce 3 phase voltages, line to line voltages similar to this vector. Here the line to line voltages could be plus VDC, one will be plus VDC and minus VDC. Here the line to line voltages will be plus VDC by 2 minus VDC by 2 and 0. That would be the difference now. The same way you can find out, you can see that there are other 2 vectors which are 0 plus 0 and minus 0 minus. Similarly, you will have 2 of the states producing a vector equivalent to 0.5 VDC in this direction. They are 0 plus plus minus 0 0. Again, this is something similar. You have 0 0 plus and minus minus 0 leading to vectors of 0.5. Here you have plus 0 plus 0 minus 0. These would be the vectors now. So, now how many vectors have been accounted for? You have accounted for another 12 more states. So, these 12 more states lead to 6 distinct active vectors of length 0.5 VDC. So, let us just say, so these 12 inverter states lead to vectors of length VDC by 2 and 3 of them lead to 0. So, you have now accounted for 21 out of this 3 power 3 is equal to 27 states, 21 have been accounted for. There are 6 other states which are combinations of plus 0 and minus, in which one pole voltage will be VDC by 2, another one will be 0 and the third one will be minus VDC by 2. Such combinations are the ones that are missing. So, those things, as we quickly discussed, as we discussed yesterday, you can see that if this is here you see it is minus to plus, there is a transition. So, you consider plus 0 minus, and if you look at this will be actually be producing a vector which is like this. And similarly, you see that this is minus and this is plus here, and so you look at 0 plus minus, that would actually be producing a vector like this. And here you see minus 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 is a transition, minus plus minus 2. So, the transition here is here. So, in between you have minus plus 0. If you look at minus plus 0 would be like this, would produce a vector like that. And here what switches? It is plus, and here it is minus. It is the y phase that is switching. So, you consider minus 0 plus, and that would be producing a vector like this. And here once again you have minus minus plus switching to plus minus plus. So, in between you have 0 minus plus, and that produces a vector like this. So, you see that you have 6 more vectors, and these vectors, these active states produce active vectors of lengths √3 VDC by 2. So, thus you can see that there are totally 21 plus 6 27 states have been accounted for. So, these states which produce vectors of length VDC, there are unique states. So, these 6 unique states produce 6 unique active vectors of length VDC, and if you look at the output line to line output voltages, their line to line output voltages will be plus VDC, 0 and minus VDC. There are 6 other states which produce 6 vectors of length 0.866 VDC. If you look at their line to line voltages, it will be plus VDC, minus VDC by 2, minus VDC by 2, or minus VDC plus VDC by 2 and plus VDC by 2 would be their line to line voltages. So, those are these inverter states now. So, these 12 vectors, their tips are sitting on this. These 6 vectors form a hexagon, and the remaining 6 vectors touch the midpoints of these sides of the hexagon. So, these 12 vectors tip, they lie on this hexagon, and there are the other 12 states produce 6 vectors which lie inside in an inner hexagon. So, this is just for us to get a clearer picture. So, it is the same idea, you have the pole voltage, there is an additional possibility that instead of plus VDC by 2 and minus VDC by 2, it can be 0 also. Otherwise, it is the same way we would evaluate VRY, VRN and V alpha, V beta and so on, and this is how we come up with the voltage vectors of a 3 level inverter. So, this is now if you look at a 3 phase voltage source inverter, you have VR, Vy and Vb. Now, you want an average output voltage in a particular subcycle, this is a small duration of time. So, in a 2 level inverter, you need this average, you are going to apply 0.5 VDC for some time and minus 0.5 VDC for remaining time, and realize that, whereas here you are going to apply 0.5 VDC and 0 to realize the same average voltage. So, as I mentioned yesterday, here you see that the error is very high, this is your error between the desired output voltage and the actual output voltage, but here you see that the instantaneous error is lower, and therefore, this indicates lower harmonic content in the voltage, and that would also result in lower harmonic content in the current. So, in both the cases, whether 2 level or 3 level, you want the RO average to vary like a sinusoid when you are doing sine triangle PWM. So, you can vary this sinusoidally, and if you can vary VRO sinusoidally, VYO and VBO sinusoidally, you vary this sinusoidally, then VRO minus VYO average would be VRY average, which will be sinusoidal. Again, VYO minus VBO average will be VYB average. Again, VBO average minus VRO average will be VBR average. So, you can get balanced sinusoidal voltages in the line to line if you produce balanced 3 phase average pole voltages. So, this is what we do using sine triangle PWM. We use modulating signals which are balanced 3 phase sinusoids and compare them with a triangular carrier. So, this is true for both 2 level as well as 3 level inverter, but the way we need to switch the carriers, there will be a difference now. So, if you do the sinusoidal modulation, these are the 3 phase modulating signals, the average pole voltages would be a replica of the modulating signals, they will be the scaled versions of that. So, this is really the what you can regard as the normalized modulating signal multiplied by VDC by 2, that would be your average pole voltage. So, you will have 3 phase average pole voltages which will be sinusoidal, and then you subtract the 2 to get one line to line voltage. Similarly, you get your VYB average and VBR average, and you also get your VRN average, which will forms this which is given by this equation. Similarly, you will have your VYN average as VYB average minus VRY average. VBN average would be VBR average minus VYB average upon 3 divided by 3, and you will see for sinusoidal modulation VRN average is equal to VRO average. And as we saw yesterday, we can also add common mode signals to MR, MY, MB and get MR star, MY star, MB star, which contains sinusoid plus some triple frequency components. In that case, VRO average would be the wave shape would be similar to that of MR star. VYO average wave shape will be similar to MY star and so on. So, the common mode exists in MR star and VRO average, but in VRY average the common mode will go away, because when you are doing VRO average minus VYO average, the common mode contained here is same as the common mode contained here, and therefore, they get cancelled out, and VRN average will also have no common mode component. So, your VRN average will be VRO average minus the common mode component. So, that is what you will get this as a sinusoidal voltage now. So, your 3 phase VRN average, VYN average and VBN average can be transformed into V alpha average and V beta average, because when the 3 sum up to 0, you need only 2 quantities to represent them. So, this is space vector transformation. If the difference comes in the 2 level and 3 level cases, that you compare it with a single carrier now. I have not shown the Y phase and the B phase sinusoids here, I have shown only the R phase, all of them are compared with a single carrier now. In the case of a 3 level, you need to do it differently. You do not have one pair of complementary switches, you have 2 pairs of complementary switches. So, you have 2 level shifted carriers, and so there is one top which runs between 0 and 1, there is a bottom one which runs between minus 1 and 0. So, the R, Y, B are all compared here. So, how do you do this? What could be the switching logic? For example, if you consider R phase, here it is greater than both the carriers, then VRO is plus 0.5 VDC, which means S1 and S2 are both high, and you take a situation here where MR is lower than both the carriers. So, in that case S3 and S4 are high. So, VRO will be minus VDC by 2, and you take anywhere in between where, like for example here. So, it MR is less than one carrier, but greater than the other carrier. In that case VRO is equal to 0. So, S2 and S3 will be on, the middle 2 switches will be on in the R phase. So, that would be your switching logic, and you can go about doing this, and this will result in sinusoidal output waveforms as you wanted here, like you will get sinusoidal outputs as you want here, and this will give you sinusoidal line to line voltages, average voltages will all be sinusoidal. Now, you can also do a phase shifting as I mentioned in the last lecture. So, whether there is any advantage or not is something that you have to see, but it is possible to do that. Now, let me do this phase shifting like this. That is what I mean is, the top carrier let it be wherever it is, the bottom carrier, the same carrier I am just shifting it by a certain small angle at this frequency. So, this is a phase shifting. Okay. So, what I can do now is I can compare this with 2 level shifted carriers, but they are phase shifted like here. So, generally this will not affect the fundamental voltage, provided you have assumed a very high carrier frequency, but this will affect the harmonic voltages now. So, a very specific case which is sometimes considered also is the out of phase level shifted carriers. Actually, what you have here is, let me use a different color for clarity. So, the top is one carrier, this is another carrier, this color is also not very clear here. So, should I use orange? Yeah. So, you can see that this is another carrier, the black is one carrier, this is another carrier. So, because I have used the same color, the carriers may not be very clear to you, therefore, I am changing that. Okay. So, here again you can use the same logic. So, for example, you can say here MR will be plus VDC by 2, VRO will be plus VDC by 2, and it is between the two carriers, then the phase would be 0, the pole voltage, and if it is lower than that, then the pole voltage can be minus VDC by 2. So, you will see that the harmonic differences are very pronounced, and some studies have also been carried out earlier, which shows that the out of phase level shifted carriers will lead to a much worse harmonic distortion than the single phase carriers now. You can actually look at it by looking at the switching sequences, which we will do it in some 2 slides from now, something that I told you at the end of the last lecture. So, before we go into that, let us take the same in phase carrier, because this is what is preferred from a harmonic performance point of view. This is very good, but the trouble here is when you have 2 carriers, you have to produce 2 carriers, one is positive, one is negative, and this signal is bipolar. So, normally it is very easy to handle if the signals are all unipolar in many microcontrollers and microprocessors. So, you can avoid. So, you can see, for example, if you look at only the R phase, you see that this part of the carrier, they do have no role at all, there is no intersection. Again here there is no intersection at all. So, let me do one very simple thing. What is that? Let me shift this up, I am showing this in kind of orange color. So, what I am going to do is, I am going to shift this up. So, this orange one is the negative R phase shifted. So, I have the same waveform here for the positive half cycle, and for the negative half cycle let me phase shift like this. So, what do I have here? What is the difference between this and that? This is same as MR. In the negative half cycle, this is equal to 1 plus MR, that is what has been done. Now, you compare. So, the comparison between this and the triangle is same as the comparison between this and triangle, there is actually no difference really at all. You should bear in mind that these are very high frequency carriers. Now, I have shown very few, only about 9 carrier cycles or so, because it is easy for me to draw that way. It is very more difficult for me to draw about 150 cycles, and it may also get very cluttered now. So, we are just shifting this part. So, now what do you need? You may not need the lower one at all. You may not need the lower carrier at all. You will not need the lower carrier at all. So, you do what is a single carrier PWM. Like we have one sine wave on 2 carriers, there are also methods where you use 2 sine waves on 1 carrier, that has also been discussed in the literature. And now, this is some modification of your in phase carrier PWM, so that you can use just a single carrier by phase shifting your things. Alright. So, this is what I have shown plotted here. So, this is something you do in your PWM generator, and you do your comparisons based on that. So, that is a easy way of implementing. So, this is very identical to what you do with 2 level shifted carriers which are in phase, and that is what we will be considering for the rest of the discussions in today's lecture and the next lecture. So, what we are actually considering is this 3 phase sine waves compared with 2 level shifted carriers, and this is equivalent to that. So, that is the PWM waveform we are going to consider. So, now let us go and start looking at what we first assumed. We said that out of phase carriers lead to higher harmonic distortion, whatever. So, for that we need to prove. So, for that we need to look at the switching sequence. So, how can we possibly do that? Now, let us say we take some levels. This is, we call this as 1, 0 and minus 1. So, we are going to consider out of phase carriers, right? Okay. So, let us say this is the top carrier, and let us say this is the bottom carrier. So, now what I am going to look at is, I am going to consider 3 phase signals. So, R, let us say the R phase signal is here. Now, I need to consider a Y phase signal. So, let me use orange here for the time being. So, let us say the Y phase signal is here, and I need to lose B phase. So, it is like here. So, the 3 would actually add up to 0. You can actually call them as MR, MY and MB, whereas the other 2 are carriers. So, they should add up to 0 if you are considering sinusoidal PWM. Okay. So, now what happens here? You have first certain time interval, you have one thing happening here. Prior to this interval, what happens? This is R phase. So, you see that the R phase is, excuse me, R phase modulating signal is greater than both of R phase modulating signal is greater than both the carrier signals. So, that is plus, it is equal to plus VDC by 2, and that is the case up to this point. Up to this point R phase pole voltage is plus VDC by 2, beyond this point it is 0. If you take Y phase here is minus VDC by 2, and from here onwards Y phase is 0. If you take B phase, it is minus VDC by 2 up to here, and from here onwards it is 0. So, if I write down the sequences, this is one switching instant, this is another switching instant, this is yet another switching instant. So, R phase is positive. Let me write down for the states R, Y, B positive, Y phase is 0, and B phase is also no, Y phase is negative. Y phase carrier is lower than both the, I mean Y phase modulating signal is lower than both the carriers, and therefore it is minus, and if you look at the B phase also it is minus. Then in the next interval R phase is positive, because the R phase modulating signal is greater than both of them. Here again the R phase is positive because the modulating signal is greater than both the carriers, here it becomes 0. If I look at Y phase minus, at this instant Y phase is switching, and then after that it is 0. So, it is the Y phase VYO is 0, here also VYO is 0, here also it is 0. And how about B phase? Initially it is minus. So, in this interval also it is minus, in this interval it is 0, and in this interval it is 0. This is what you get. So, your inverter state sequence starts from plus minus minus, and next it goes to plus 0 minus, and from there it goes to plus 0 0, and there it goes to 0 0 0. And you will see that in the next subcycle, if you consider the next half carrier cycle, the same thing will happen in the opposite direction. From 0 0 0 it will go to plus 0 0, from there it will go to plus 0 minus, and from there it will go to plus minus minus. This will keep happening when for half a sector or so on. So, this is the nature of variation in the inverter states. Now, let us look at how it varies for the other one. That is, let us look at this in the space vector plane. Okay. So, we have 0 0 0 is here, we have then plus 0 0 which is here, and we have plus 0 minus and plus minus minus. Plus minus minus is here, and plus 0 minus is here. This is plus plus minus plus 0 minus. So, the nature of state transition here is you start from here, then here, then you go here, this is 1, and in the next subcycle or so you will come back in the opposite direction. So, this would be your sequence. This would be how you are going to change now. So, let us say where will the average vector be? The average vector can be anywhere here, the average vector can be anywhere within this. So, that will be bound by these tips. So, the average vector can fall anywhere within this one. Now, let me say the voltages are such that the average vector is here. Let me choose some other color. So, the average vector is here. So, now what happens? You look at the error, this error is small, this error is small, this error is small, however, this error is quite large. So, you have a large error coming up here. So, that is one reason why the harmonic distortion is quite high. The same way, if you try to do it for these switching sequences for in phase carriers, you have 1, 0 and minus 1. So, let us say the carriers are in phase. So, the top carrier is rising. So, let us say the bottom carrier is also rising. Then let us say we go in for red color, and let us say this is MR, the R phase modulating signal in this half carrier cycle. Then let me say I will go to Y phase, this is the Y phase modulating signal in this carrier, half carrier rather. Then this is B phase, let me say this is the B phase modulating carrier here. Okay. So, now you have like this. What are we going to do from here? We are going to look at the various switching transitions. When are the switching transitions going to occur? So, you have one switching instant here, then you may have another switching instant occurring here, and you have a third switching instant occurring here. So, what are the various in this interval? If a first interval I consider, R phase is modulating signal is greater than both the carrier, and therefore, this will be positive, and here also the R phase would be positive, and here it is 0, and this is again would be 0. And then if I look at Y phase, in this case Y phase is being compared with the bottom carrier, it can actually be 0 or 1. Initially Y phase is 0, here also it is 0, here also it is 0, and here it becomes minus. Then if I look at B phase, initially it is 0, then here it switches and it goes to minus, and it is minus, and it is minus. So, how does the inverter state change? From plus 0 0, it goes to plus 0 minus, and it goes to 0 0 minus, use 0 minus minus. So, this is how it goes from here in one direction, and if you look at the next sub cycle, it will probably go in the opposite direction. So, you can see that all these are neighboring vectors. You can see everything is away only by one switching, here only B phase is switched, here only R, and then. So, there is one switching per state transition is something automatically ensured by most of these methods. Any well designed method will actually ensure that. If you are doing it in the space vector method, and you will construct your sequence assuming you are enforcing this particular condition, you will not unnecessarily switch, let us say 2 phases or 3 phases together for a particular state transition. So, now this is plus 0 0 plus 0 minus 0 minus 0 0 minus and 0 minus minus. Now, let us say I look at a similar one. Now, this is plus 1 0 minus 1, these are the two carriers, and let me look at a low modulation index. So, low modulation index meaning I may have my MR like this, this is my MR. Let us say I am having my MY, MY is like here, and let me have my MB, MB is like here. So, there are a number of switching transitions. Where are the switching transitions? This is one, and this is another switching transition, and this is yet another switching transition. So, if you look at the R phase is initially positive, and then it switches to 0, here it is all 0 0 0. Then if you look at Y phase, it is initially 0, continues to be 0 0 and becomes minus. If you look at B phase, it is 0 0 and it is minus and minus here. So, this is how they are transitioning. So, that is it starts from plus 0 0 and goes to 0 0 0 and goes to 0 0 minus and then 0 minus minus. The same thing will happen in the opposite direction in the other thing. So, it starts with plus 0 0 goes to 0 0 0, you look at what happened briefly, plus 0 0 it went to plus 0 minus, 0 0 minus and 0 0 thing. So, you see that it is different. Why is it different? Because the modulation indices are different. So, but in both the cases there is one similarity, these vectors as also these vectors, they are all neighboring vectors. Let us go on the space vector plane. Let me draw that here. What happens in so So, if I say plus 0 0, 0 0 0, 0 0 minus and 0 minus minus, every time whatever I may do, what you will find is, you will find depending on case by case, for many cases that you may consider, these would be the 3 vectors applied, or these would be the 3 vectors applied, or these would be the 3 vectors applied, and these would be the 3 vectors applied. That will depend upon the average voltage vector. You have the 3 phase modulating signals, you can transform it into the space vector domain, and in this space vector domain, if you see that your reference vector is here, sorry, if you see that your reference vector is here, you will see that these vectors would have been used. On the other hand, if your reference vector is here, you will see that these 3 vectors get applied. The same way, if you let us say your reference vector is here, you will see that these vectors get applied and they go around this. So, these are what you would call as the 3 nearest vectors, and the in phase sine triangle PWM makes sure that the 3 nearest vectors get applied, and therefore, you have a very good harmonic distortion. You can find something work in this, particularly comparison of in phase and the out of phase carrier in the first paper, which is presented in the National Power Electronics Conference, and this is the later study. It is a follow up on the previous work is the other one, which was presented again in the National Power Electronics Conference in 2011, and this PhD thesis by Soumitra Das contains a chapter which is really this comparison of these various methods now. So, what we can actually see is you can also add common mode components to that. For example, you can add third harmonic component, you can add certain common mode components which will result in bus clamping, the so called discontinuous PWM, and different continuous and discontinuous modulating signals are possible with 3 level inverter. In 2 level inverter, you can clamp a phase only to the positive bus and the 0 bus, negative bus. Here you can also clamp to the 0 bus, that is some interesting possibility you have, and you can compare these 3 phase modulating signals with in phase triangular carriers. So, this is what we would look at now. For example, if you see this, there is a third harmonic injection, compare them with 2 level shifted carriers as before, you get your PWM. So, what will happen is the pivot states, the so called pivot states there, the time for which they are applied will be the same 3 nearest vectors will be applied. You will see that one of the vectors get applied twice. You may see it is always starting from here and ending back here. That vector is both the 0 states are used, that time division will change, that is what you will observe now. It is actually interesting to do these studies also, and this switching sequence, what happens is this is pretty similar. If I want to analyze that, is similar to sine triangle PWM. What we did here in sine triangle PWM, you can consider the same way. Let us say like this, you add a small common mode, maybe positive common mode or negative common mode, and do the comparison. What you will get, this plus 0 0, this instant may, all the 3 instants may shift to the left or shift to the right. So, the time for which plus 0 0 is applied and 0 minus minus applied, they will change, but their sum will remain the same. So, we call this pivot vector, this is 0.5 VDC, this is the same 0.5 VDC length vector, this is we call pivot vector, and these 2 states are called pivot states. Like the division of 0 states changing, here the division of pivot states will change. The same thing you can also do with the 60 degree bus clamping method. You can do an analysis. So, this R phase will be here and the Y phase and the B phase signals will be lower than that. You can look at the switching sequence for bus clamping PWM like we did for sine triangle PWM. You can consider this as an exercise for yourself, and so you can see these various switching sequences for carrier based PWM methods. They have been analyzed in this thesis. So, this is a useful reference for you. So, we would actually see this is the complete set of voltage vectors which we discussed before. They look like this. And when you go in for space vector based PWM, which is an extension of the space vector based PWM for 3 level inverters, but you have a few issues, because in every sector you have multiple triangles, and in each triangle you will use this one, in another triangle you will use this vector, and so on, and the calculations are all different in different triangles. That leads to some difficulties, and therefore, you start viewing a 3 level inverter as an equivalent 2 level inverter. So, like only this hexagon, and this is something which we would look at in the next class. Once you consider this as a 2 level inverter, the PWM implementation becomes fairly simple as delineated here. I will discuss this in more detail in the next lecture. So, these are some useful references in that regard. There are a couple of references that I have indicated here. So, you could look at those references for this thing, and I will continue this in the next lecture. Thank you very much.